Stanton from Synapse, sorry. Hopefully we've got all the technical stuff working and you're all hearing me and seeing our first slide up. We're doing a webinar today about emissions displacement and the Clean Power Plan. And our speakers are going to be two Synapse staff members, Allison Napoleon and Needy Stanton. Before we get going, I'm going to just talk a little bit about webinar logistics. So the webinar is being recorded. We're going to send that recording and the slides out to all the participants. All of the attendees have been muted, so we're not going to be able to hear you, but you can hear us. And that means that if you have a question, you should send it to us on the email that you see right here, which is webinar@synapse-energy.com. So those are for your questions about content. If you're having a technical problem, please use the chat feature for WebEx, and our technical person will help you out with that. We're going to have a presentation for about a half an hour, and then we're going to switch over to questions and answers. So I'll start going through, I'll keep an eye on the webinar at Synapse email throughout the presentation, looking at your questions as they come in, but I'll start to ask them of the presenters after that half an hour has passed. So again, thanks for joining us, and turn it over to Alice.
There's one more, actually. Okay. Hi, my name is Alice Napoleon. I'm a senior associate at Synapse Energy Economics. Just a couple words about Synapse. It was founded in 1996 by Bruce Dewald. It's a leader for public interest and government clients in providing rigorous analysis of the electric power sector. And we have a staff of about 30. Including experts in energy and environmental economics and environmental compliance. So my name is Alice Napoleon. I'm a senior associate here at Synapse, and I've been with Synapse for over 10 years. I specialize in energy efficiency and the benefits that are associated with that, including reductions in emissions. So I've forwarded to the first slide in our content slide in our deck. Let's jump in. Presenting a highly simplified model, stylized picture of the impact of renewable energy and energy efficiency also has similar effects on the electric power system in terms of CO2 emissions, that is the greenhouse gas carbon dioxide. On this slide, we can see conventional fossil fuels, fuel resources, as well as, and those are depicted by, on the left side of the scale, you can see 3 little power plants, as well as wind and solar farms, or any kind of wind and solar resources, really. The demand for electricity is shown as people on the right side of the scale. In this picture, the amount of electric supply in terms of megawatt hours, which and demand is currently equal. If we add more solar and wind, in this picture you can see it's in green, the amount of supply would be greater than demand. That is, if demand is held constant. Electric systems must be in balance at all times, however. System operators make sure that supply and demand balance minute to minute, 24 hours a day, 365 days a year. Who are these system operators? For example, we have regional transmission organizations like PJM, New York ISO, ISO New England, California ISO, and also some vertically integrated utilities in some areas of the country perform this function. And how do they balance the resources? Well, one way that they do that is by telling resources to increase or decrease their production. That is those plants that you see on the left side of the scale. So system operators generally dispatch resources with the lowest operational costs first. This slide shows a hypothetical supply curve. the wind and solar resources don't have fuel costs. They generally produce whenever wind is blowing or the sun is shining for no additional cost. They are the lowest on the supply curve. You can see them all the way on the bottom left-hand side. Higher on the curve, you'll see conventional plants, which might be burning fossil fuels. The fuels add additional costs, and so these plants have operational costs, which make them a little bit more expensive to run. You can see a horizontal line. It's a blue line representing demand. That is instantaneously what all the collective demand from our refrigerators and our motors and all of the other things that we use electricity for, what that level is within this particular hypothetical system. In this example, one plant is not dispatched. That plant is all the way on the top right. And then one other plant that I did want to point out is the marginal resource, which is, if you guys can see my cursor, it is the one right, okay, good, you can see it. It's the one that I'm pointing to with my cursor. It's immediately below the demand curve. It's the last resource that gets, is actually dispatched. It's the most expensive resource that is actually dispatched. Okay, so what happens if we add more resources with low running costs? New resources are shown in green here in the bottom left. These also have low or no cost to operate, like the other renewable resources that we saw earlier. And now we can see that they bump out the curve, the supply curve. So now 3 plants, all of them are conventional fossil fuel burning power plants, are no longer needed. The system operator tells the 3 plants that are above the line to stop producing. The one that's on the line may be told to reduce production, but it won't be told probably to shut off. I should say that this is a really simplified example where we're only considering cost. There are other factors that come into play with this. For example, reliability or limits on how plants can be operated. So some plants take a long time to ramp up to full production or to ramp down, and those system operators need to take those characteristics of power plants into account when they're deciding who to dispatch or which plants to dispatch. Reliability just refers to the ability of the system to serve all the needs based on demand in a reliable fashion. And so system operators might decide to operate one plant that's closer to load, or excuse me, closer to where most of the demand is, as opposed to another one that's farther away. So those are just some examples of the other constraints, of which there are many, that system operators must take into account. So far we've been talking about instantaneous balancing of supply and demand, but we can envision that demand grows over time, as historically has usually been the case, and that is without aggressive energy efficiency. In the future, demand may be higher, shown by the dashed line. It's a pink line. We can add renewable resources to our hypothetical supply curve. As before, they bump out the curve, but in the future, all would run except the plant in the upper right. If it's no longer operating in most hours, the plant owners may decide if they want to retire that resource, or it may not run most of the hours. Thus, renewable energy or other low-cost resources can have an impact on future decisions on whether to retire existing resources, or whether to build new fossil-fired generation, or to defer construction of new fossil-fired generation. So the reason why we are having this webinar is Synapse my colleagues and I conducted some research to make sure to see if the hypothetical example that I've been telling you about for the last few minutes is actually what happens. We've been looking to see if new energy efficiency and renewable energy actually does displace fossil-fired generation resources that are on the grid, and looking for evidence of whether emissions reductions are associated with the renewable energy and energy efficiency additions. So some of the areas that we considered, and I don't think I have enough time to go into all of them, but I will give you a little taste of them. We looked at national studies, including the Energy Information Administration's Annual Energy Outlook. That's an annual publication by EIA that looks at scenarios with increased energy efficiency or renewable energy. That might be through increased penetration of energy efficiency or renewable energy due to lower costs, or increased technology development beyond some base level that is anticipated. And that's a forward-looking analysis. We also examined Synapse modeling of clean power plant scenarios. Again, that's a forward-looking analysis. And we can also point to other studies that also demonstrate that emissions can be displaced by energy efficiency and renewable energy. We also examined integrated resource plans. Those are plans completed by utilities, or excuse me, they can be completed by utilities. They look at future supply and demand energy resources in general, and the way that we looked at these was similar to the AEO. We considered cases that had increased penetration of energy efficiency or renewable energy. We looked at regional transmission organization studies. These are historical studies that look at the marginal resources, that is, the resource that's most expensive that, all else held equal, would be displaced if new, less expensive resources are added to the system. And so these are at the regional level. They're put forth by entities like PJM Interconnection and ISO New England, and they look at what the resources, the percentage of time that different categories of resources are so-called on the margin. And then something that NEEDY, my colleague will talk about a little bit more, is the U.S. EPA's avoided emissions and generation tool. So let me turn now just to a quick look at the energy and the annual energy outlook research that we did. So here we've got 3 scenarios that you can see from Annual Energy Outlook. We looked at the best available demand technology, the high demand technology, and the low renewable cost technology, or low renewable cost scenarios for Annual Energy Outlook. The graphs that you're looking at are comparing energy production relative to a reference case, the 2014 reference case for AEO. Reference case is basically what AEO, or EIA actually, expects to happen. It's, in their estimation, the most reasonably anticipated future case. And so we compared that case with these other 3 scenarios, which include higher levels of energy efficiency penetration and also a higher level of renewable penetration, that being the low renewables cost. And you can see from these graphs that as the amount of energy output from renewables increases and as demand is reduced by energy efficiency. You also see a decline in the emissions of carbon dioxide associated with each of these scenarios. And I think we're probably a little time constrained, so I'm going to turn it over to Needy for the next portion.
Thanks, Alice. Just before I begin, we just wanted to take one moment to remind everyone to please send any questions you have about content to webinar@synapseenergy.com. And any technical issues that anyone is experiencing with the WebEx software, please use the chat feature and we'll get that resolved for you right away. So quickly about me, my name is Needy Santon. I'm here at Synapse on the staff. I'm one of the authors of the Displaced Emissions report that Alice was just describing to you a moment ago. I'm an electricity system modeler, and I'm one of the many people here at Synapse who have been digging into the Clean Power Plan and what displaced emissions means for us when we think about CPP. So I'm going to go over what we did research-wise with the AVERT tool. This is described in more detail in the paper, which I have listed at the bottom, and I'll go into that in 1 second. But under contract with the EPA a couple of years ago, Synapse helped build AVERT, which is the Avoided Emissions and Generation tool to estimate displaced emissions around the country. This is our basic schematic for AVERT. I'm not going to go into any detail about the actual tool, but wanted to just give you the overview of it to show you how it's basically an intermediate level energy system modeling tool. We can think about how there are many different ways to estimate how injecting new energy efficiency or renewable energy on the grid can cause displaced emissions, displaced production from other units on that grid. AVERT is one of these tools, and it's particularly valuable because it does fall in the middle of this spectrum in terms of user-friendliness, level of sophistication, and it's driven entirely by publicly available data that the EPA has. Some of the key references I've listed down at the bottom of the slide. You can download the tool and the user manual and check it out at EPA's website. You can read a recent academic conference paper that Synapse wrote with EPA that was presented at the annual Emissions Inventory Conference in San Diego this year. The link to our Displaced Emissions report is there as well, and EPA also has a link to AVERT on the Clean Power Plan Toolbox for States website. So with this tool, we ran a series of case studies to explore how different types of energy efficiency and renewable energy programs can displace emissions on the grid. The advantage of using a tool like AVERT is that it is national, and so AVERT has 10 different regions that it represents around the country. And the table on the top of this slide shows those different regions. And we systematically injected different types of energy efficiency and renewable energy programs into the grids that represent the regions in AVERT. What we see in the orange highlighted rows is that overwhelmingly what our case studies are showing is that as you increase the amount of fossil, particularly coal, resource in the generation portfolio across the regions of the U.S., you are seeing higher levels of displaced emissions rates. So up in the table, what we are seeing are rates, tons of CO2 by megawatt hour of generation. So for every 1 megawatt hour of renewable energy, how many tons of CO2 are displaced in those regions? We see that in the Great Lakes, the Midwest, Rocky Mountains, and Northwest, correspond to the greater percentages of coal resource in the different generating portfolios, and that's shown on the graph on the bottom. In hindsight, this seems pretty obvious, right? You have more coal on your system, it runs more. When you add other clean energy resources, that's going to get bumped. What's nice about AVERT is that we can quantify this, and we can see how it really is geographically varied around the country. What we also need to take away from this is that displaced emissions then are not created equally, right? So 1 megawatt hour of renewable energy in the Northeast is going to displace a different amount of CO2 than 1 megawatt hour of renewable energy in the Great Lakes. We did take care to inject the same amount of resource potential for each one of these programs, and we're still seeing these differential rates. This brings us to CPP and why this all matters. So for those of you who joined our previous webinar, you've seen a version of this slide before where we talked about EPA and its changes to the best system of emission reduction from the proposed rule to the final rule. On the top shows the proposed rule's emissions rates and its inclusion of renewable energy and energy efficiency in the denominator of the proposed rates. And then the bottom two sections show the fossil steam emission rate and the NGCC emission rate that are associated with the final rule. And NGCC being natural gas combined cycle units. Renewable energy is still part of the best system of emission reduction that went into these equations. Energy efficiency is no longer part of this goal-setting part of the rule. But what's important is that the renewable energy is not the same when moving over from the proposed rule to the final rule. In this case, the renewable energy generation that comes into the denominator of the emission rates for fossil steam and NGCC are explicitly displaced generation. So it's the renewable generation, the portion of renewable generation that displaces either fossil steam or NGCC. Another way to see this visually is in looking at the schematics on this slide. So the top schematic is of the proposed rule and its approach to EERE, and the bottom shows the schematic associated with the final rule and its approach to EERE. Where if you think about the top portion of these graphs as the level of demand, in the proposed rule, energy efficiency and renewables counted as one of the different components that could be used for compliance with the final level of emissions. In the final rule, the approach is very explicitly that the renewables and energy efficiency squeeze out the natural gas and fossil. And so it is very explicitly a displacement mechanism that the EPA is considering. You've also seen this slide on compliance, and this is where the wrinkle begins, thinking about displaced emissions in the Clean Power Plan. EPA has been very explicit to include displacements in its goal setting and in setting the targets for fossil steam and NGCCs. When thinking about compliance pathways and what states are going to do to show, to demonstrate compliance with those rates, there's lots of different compliance pathways now, and we're not going to go into all of these, but we're going to focus on one particularly to show you where displaced emissions comes in. So we're going to focus on a rate-based compliance world, R1 in particular, where EGUs are complying with subcategory-specific emission rates, and these are nationwide emission rates for these two units. In this world, we're measuring rates in pounds of CO2 per megawatt hour, and these are applied at the EGU level, not the state level. And again, these are nationwide rates for NGCCs and fossil steam. The equation for this is that the units will have to comply with is their stack emissions on the numerator divided by the generation, the electricity they produce, plus the emission rate credit, reduction credits, or ERCs, that are available to them. So these ERCs act as a way to dilute the rate at the stack, at the unit, and is a way that EPA is explicitly allowing energy efficiency and renewable energy to come into the compliance, to come into the compliance pathway. The next two bullets are important in that ERCs can be produced by renewables, energy efficiency, a whole host of other technologies and generation pathways, nuclear units, capacity uprates at nuclear, hydro, and NGCC plants. There are limitations according to the different specific compliance pathway and the different types of arrangements that states are going to take. But in general, for each type of compliance pathway, these ERCs can be traded between EGUs in any state using the same compliance approach. So where this leaves us is that if we think back at what we've talked about in this webinar, renewable energy and energy efficiency can displace emissions. But we've talked about how those displaced emissions are geographically varied. So we've talked about these displaced emissions not being created equally. This then means that displacing a megawatt hour of generation in the Northeast, for example, is going to reduce a different amount of CO2 than displacing a megawatt hour in the Great Lakes. When ERCs are tied to the megawatt hours that are displaced, that are generated by the renewable energy in these specific regions, we can close the loop and tie that back to the ERC itself is not created equally. And so what this, where this leaves us is that with a wrinkle to potentially deal with as states think about compliance. We have the potential to comply with the performance rate because we can use these ERCs that can be traded across states within different regions. But this also potentially places a stress on the policy goal of CPP itself because the CO2 associated with those ERCs are not the same. I think that's all I have. Liz, I'll give it back to you.
Great, this was great. I'm just going to go over a little bit of general information and then we'll dive into some questions. Thanks both of you for a really good presentation on this complicated topic. I want to just mention a few slides that are here in the deck for your reference later. Synapse is in the process of putting together its modeling capabilities for the new rule to be able to perform analysis on Clean Power Plan compliance for both states and stakeholders. So there's information about that on our website. We also have a lot of other resources available to you. You'll see here the first one in this list is the paper on emissions displacement that Allison and Needy have been talking about. They went through some parts of it. There's a lot more information in there. So if you're interested in this topic and want to get a deeper dive, please go ahead and download that. And you'll see some other resources here. A lot of these are about the proposed rule because we're still at work on producing materials on the new rule, but they're still useful for background information. We've also had some good blog posts that you'll see up on our website that are about the new rule and are helpful to breaking that down and understanding the information. This webinar is part of the of a series of weekly webinars that we're doing. Next week, we're going to be presenting a detailed treatment on the final clean power plan, breaking it down and hitting the most important topics in it in some detail. And you can see some topics going out into the future. The nearer ones are more certain than the ones that are further out. There may be changes, so stay tuned and check out the changes as we go along. We're going to switch over to doing questions and answers. I'm watching the webinar at email and have had some questions come in. There's plenty of room, I think, for more if people want to send them in, and I've got some other ones lined up here. We are joined in the room by an additional Synapse expert, Sarah Jackson, who you may have heard on other webinars. So she can help us out. She's one of our Clean Power Plan experts and can help us out answering questions as we go along. So I'm going to start out with a few things here. First, just to help everybody understand, you're saying that not all ERCs, the megawatt-hour trading tool, they're not all created equal. So if for example, the ERCs are associated with renewable energy or with energy efficiency. If I generate a megawatt-hour of renewables in the Northeast, how is that different to generating a megawatt-hour of renewables in the Southeast?
Mm-hmm. So to be very explicit, so it's a good question because it does. We will benefit from being very clear about that. From the perspective of compliance and what the EPA is allowing in this rule, there's no difference from a compliance standpoint. The megawatt hour that generates that ERC is the same when it enters into the denominator of the performance rate that in the example that we saw the EGU will need to comply with. From the perspective of the CO2 ton that was associated, or fraction of a ton, that was associated with that creation of that ERC, it is very likely not the same because the CO2 that was displaced on the system that the ERC was created in is very likely different than a different amount of CO2 that was displaced in the system that ERC is going to be used in for compliance.
Okay, so it's just different points of view. From the point of view of a state that's complying with the Clean Power Plan, I could buy an ERC from, if there are some limitations on this, but I could buy an ERC from the Northeast or buy an ERC from the Southeast. It's 1 megawatt hour. It's just 1 megawatt hour.
Yes.
But if instead I'm interested in the amount of total CO2 emitted from the United States, then those two things could actually be different from each other.
Yes.
So, okay. Here's another kind of basic question to help get our heads around this. So if I build a wind turbine in my backyard, what am I displacing? Am I displacing the energy from the coal plant down the road? Am I displacing a little bit of every coal plant everywhere? What am I actually displacing?
Hi, this is Alice again. So you aren't actually displacing or not necessarily displacing the power plant that's down the road. So the energy system doesn't know the jurisdictional boundaries that we've established in the U.S. It's much more governed, by the system operators. So the decisions that the system operators make is going to determine which plants are backed off. And as I mentioned, economics is a big part of that decision. But there are also other factors like reliability and operational characteristics of the power plant that is on the margin. The most expensive one may not be backed down if there are other operational constraints. Some coal-fired units take a long time to ramp up and ramp down. Nuclear units are generally not very flexible. So the decision that the system operator makes about those kinds of resources, they're not going to say, you know, turn on, turn off, turn on, turn off to one of those types of resources. On the other hand, there are more flexible resources. We typically call them peaking resources. They tend not to be the most efficient. A lot of them are natural gas fired, but they have characteristics that allow them to readily increase production on a very fast basis and decrease production on a very fast basis. So all of those considerations will come into play with whether that power plant down the street is actually being displaced.
Yeah, okay, that's really helpful. And so just thinking about it geographically, though, for my backyard wind turbine, the energy from that, am I going to displace potentially coal plants on the West Coast? Like, what are the geographic boundaries for that? How far away can I displace something?
So, yeah, you're not going to be displacing anything on the West Coast. I can guarantee that because the systems are totally separate. It's likely that you would be displacing something that's closer, much closer. And I don't know if there's anything else you wanted to add to that, maybe.
I would perhaps add that the likelihood of displacement decreases the farther you go from your backyard as a very, very rough rule of thumb.
It's pretty well regionally bounded by our ISO regions, but maybe it could extend throughout the interconnect. So for us on the East Coast, that would be most of the east up to the Rockies, right? Something like that, in theory.
In theory.
Yeah. We've got a question about nuclear generation. So this is really different in the new rule than in the proposed rule, and I know that we're still getting our heads around it. Do any of the three of you are able to speak about emissions displacement in nuclear, the differences between sort of what if there were a new nuclear plant build, what about uprates, how should we think about nuclear and emissions displacement?
You want to clarify uprates, you mean if they are improve the efficiency of the
of an existing plant.
An existing
nuclear plant. If you take an existing nuclear plant and you improve it in some way so that it's able to generate more, then that's often called an uprate. Oh. Yeah.
Hi, this is Sarah Jackson. I guess we are, as Liz said, still wrapping our heads around all these new pieces of the Clean Power Plan, but nuclear has now been existing, and under construction nuclear was taken out of the building blocks, so it's no longer part of calculating the targets for states. So new nuclear and any uprates would be essentially a compliance mechanism, and a state who were choosing to build a new nuclear plant as a compliance option in its plan would have to then look at what types of energy would be displaced. I'm not entirely sure at this point how EPA has treated that and how ERCs are generated from nuclear plants. So that's something we'll have to get into, I think, next week.
Right.
And we have had a chance to dig in more.
Yeah, so tune back in for that one next week. Did you want to say something, Nina?
No, just I wanted to put a slide up where we do very clearly see that that the new nuclear units and its uprates come into the denominator in just so everyone has the visual in front of them.
Right. Okay. Can we talk about the example for a second of two states where there is generation in one state that normally serves another state? So maybe there's a power purchase agreement in place, or maybe it's just that's normally the flow. How do we think about that with emissions displacement?
The EPA does have, in the final rule, they have been explicit that there's not going to be trading allowed from neighboring states that are under different compliance mechanisms, using different compliance mechanisms. because of the potential additional wrinkle there with emissions changing in one state and generation being used in another state, particularly when you, and then the additional wrinkle when you overlap that with the ERC, because we're talking about clean energy like renewable energy or energy efficiency. In the case where there is a power purchase agreement, even between states, there will be a mechanism allowed for using a megawatt hour in one state that was created in another state. But there's the very explicit provision that the state has to demonstrate and show the PPA exists.
Mm-hmm. Let's turn to slide 11 for a moment. We have a question about that. This was the slide showing the research from doing comparisons of scenarios from AEO. Can you just walk us through this a little bit more slowly? I think the question is wanting to understand better what the different scenarios mean, which one has more and less energy efficiency. What's going on with this is showing a difference in generation at the top, is that right?
Yes, this is showing, the line is the difference between that scenario as labeled. So the top one is the best available demand technology, the high demand technology, and the low renewable costs are each of the lines. And those are representing the difference in the renewables case between the, the generation and by renewables and the generation in the base case or the reference case.
So this is just renewables generation. It's not all. It's not total generation, I think, is what the confusion is here.
Yeah, it is the generation or the avoided generation by energy efficiency.
So this is just the energy efficiency component up here. So
yeah.
Extra. So the more that is avoided through energy efficiency, the lower the emissions is the relationship that we're seeing?
Yes.
Okay, that's what the question was about. So
yes.
Do you want to say anything more about that? Or
I could, yes. Also, the best available demand technology is a scenario in which energy efficiency is really aggressively pursued. High demand technology is less of a less penetration than the best available, but it's still higher than what AEO defines as the reference case. And then the low renewable cost is where they assume advances in technology and reductions in costs beyond what's reasonably anticipated by the Energy Information Administration.
Thanks. Here's a question that I think I'll just read to you. So I understand that ERCs achieve fewer emissions reductions when they displace generation in cleaner regions. But why is this an issue? I could see it being problematic if a coal plant in Ohio could buy an ERC from a solar farm in Massachusetts, but is that a realistic concern? Are we worried about trading over those distances?
I think the issue is that it could be an issue, and that's what we wanted. That's the issue. That's the point we wanted to raise with the research that we did and what's and the way that ERCs are included in the equations of the final performance rates. When we think about rate-based compliance as opposed to mass-based compliance, which does close a lot of the loopholes and the themes there. But when we think about rate-based compliance and how you can comply with a rate where your generation is still increasing, that means that your numerator can also increase. So when we're thinking about total tons, the mass of CO2 being released, and the overarching policy goals of the CPP, that's where it becomes an issue. If you can comply with rate, but still have more CO2 in the air, and everybody, this is an exaggeration, but everybody is doing that, you do end up with more CO2 in the air than you would otherwise end up with. So I think that's the point we are trying to bring up today. Is it in reality going to definitively be a major problem? We don't know yet, but it's something that we wanted to bring up because it's something that I think we need to pay attention to and make sure we deal with properly when thinking about demonstrating compliance at the state level.
Mm-hmm. So one place where this could be an issue, I think, is for a state that chooses to comply using a mass-based option, and it points to the importance of doing modeling, electric sector dispatch modeling, to actually see what's happening out there, because we can't just assume that new renewables and new energy efficiency is going to have a certain kind of emission effect, that you actually need pretty detailed modeling to see what the actual emissions effect is likely to be. Mm-hmm. Here's another question. What about variation in avoided emissions for different renewable technologies, solar and wind? Mm-hmm. Is that something that you've looked at?
The modeling that we did for the displaced emissions report, we very specifically injected on purpose the same resource potential. So over the course of the time horizon that we modeled, the same amount of megawatt hours was being represented by the different programs. But we actually did look at what I didn't show on the slide, but what is in the report if you download it and dig it up, is that the profiles, the temporal profiles of the different energy efficiency and renewable energy programs that we modeled were different. So we were actually modeling the intermittency in wind, and we were modeling the difference between a portfolio energy efficiency program, lots of lighting controls and appliance standards, that might take off a certain component of load off the top versus a more kind of aggressive injection of demand, fast energy efficiency that would shave off peaks a little bit more. We did look at the difference, and overwhelmingly the results are the same. So they had minor differences in how much displacement there was within a region, but overwhelmingly the results show that the issue is a geographic variation instead of a variation between different types of EE and RE programs.
Now you've got me wondering why that is. It's not the case that natural gas is on the margin everywhere and every hour. Can you talk about that a little bit?
Yep. So we did think a fair amount about that when we saw those results. And so the AVERT model is very explicitly great for regional emissions displacement work. So thinking about estimating, not by the unit and not in a very kind of rigorous level of detail of how electricity is flowing around that grid. If it was a much smaller region that we were modeling and we were able to actually model using sort of the right-hand side of that spectrum that I showed you about with energy system modeling, we would see the differentials in how the displacements happen temporally much more than we were seeing in AVERT, which is an aggregated model, and it's not only aggregating by time, but it's aggregating across lots of different units. So it's not that the issue's not there, it's just that it does get washed out quite a bit in the AVERT level model. And so what we see in AVERT is is this geographic variation. If we moved over to a much more detailed level model, we would, I assume, still see that geographic variation. We would also see the temporal and sort of like unit level variation.
The variation by resource, for example. And would you anticipate that those results would change over time as renewable penetration increases?
I do think that, so now we do have to be very explicit that we're going to move out of AVERT land, because AVERT is a great tool, and it is used for kind of short-term estimation of displaced emissions. We're not going to be using AVERT to think about what's happening on the power system and displaced emissions in 15 to 20 to 30 years. The system, AVERT is a statistical model. It's driven by behavioral relationships between different units, but it's all based on historical information. And so including what that transmission grid looks like right now. When we move 10 years down the road, that grid is very different. The units are very different, so we can't really rely on the same methodologies, not the exact same model. I will say that it does seem very clear that there is a point of diminishing returns when it comes to displaced emissions. And that's not a bad thing. That just means that the more fossil we push out and replace with clean energy, the less opportunity there is to displace more carbon. And so I think, if I remember the question, it's just that are we going to see changes in sort of those displacement rates as we move through time? Absolutely, if we get more EE and RE on the grid.
Good.
I just wanted to add to Needy's excellent response that part of the reason for looking at different pieces of evidence, the ones that we did look at in the report, is because of looking at this not from, different ways of cracking it, but there are different perspectives on this. So we've got the utility level where we looked at integrated resource plans, and that's forward-looking. We've got looked at RTO studies where they looked at the marginal resource, and these that you're seeing on the screen right now are the displacement rates that are implied by the amount of time that the different resources are on the margin. You can see here for PJM, these are percent of hours that the different types of resources are on the margin. So in 2011, the coal resources were on the margin close to 70% of the hours, and that's declined slightly. We can go talk about maybe why that is that it declined slightly, but we've seen a growth in the number of hours that the gas resources are on the margin in PJM. So it is not universally true that in all hours gas is on the margin. In fact, coal is frequently on the margin in the off-peak periods, and gas, because peakers, that is the units that are serving the load when it's at its absolute highest during the day, those tend to be gas CTs, combustion turbines, that are used or burn gas rather inefficiently, but they can respond really fast to changes in the amount of demand that's out there. So we did look at these from different time profiles and different geographic profiles because it is an important, those are two very important dimensions.
I think I can squeeze in two more questions. So first, if AVERT isn't the tool that's going to help us understand emissions displacement throughout the Clean Power Plan compliance period, it's really a tool for perhaps the next 5 years at the outside. What are the kind of tools that people listening are going to need to familiarize themselves with? What kind of tools are we talking about that can help us model displacement out 15 years?
That is the million-dollar question. So that's an excellent, excellent question. Right, AVERT is a very good tool. It allows us to do this regional emissions displacement quantification in the short term. Short-term compliance, also part of CPP. I mean, if we can think about the AVERT methodology actually working if we change the historical data, if we update the historical data as we go along. As long as we do that, we're okay. In terms of modeling longer term, thinking about the interaction between the units that are going to be generating electricity and what can potentially replace them and operations, we do need to start. EPA has been very clear and very flexible in the model about not prescribing certain types of models by name or even by fundamental kind of capability. What they have done in the rule is be very explicit about what the model needs to be able to not specific functionalities, but what the model needs to be able to give you. Our current assessment of that is that states are going to need some fairly rigorous operational electricity dispatch modeling to understand how the injection of renewable energy and these other types of generating resources that are going to create these ERCs and displaced emissions will push other units. And a longer-term capacity expansion type of planning model to understand how new units are going to come onto the system and replace old units, either retiring units or units that are otherwise pushed out for economic reasons because of the new rule.
I want to do just one more question. We'll have to do it quickly. So this is, we were talking before about what's the worry about ERCs displacing more, displacing less. How does that end up being a worry? The question is, are we suggesting that EPA may not meet its CO2 reduction goals because of these differentials? Is that the scenario that we're imagining, sort of on the macro level, if all of the ERCs were bought from one region, do you end up not meeting your CO2 goals, or what are we talking about here?
I personally don't know how the numbers are going to play out, but if I was to paint, if I was to take the point that we brought up and we've been talking about here to the most extreme level, that is the question that's on the table. Is this an issue of stressing the policy goal of CPP in the first place? How that's going to work out with the numbers, I don't know. We have not worked those numbers out.
But I would offer that if more and more new generation, renewable generation is created in one spot, one already clean area, that at some point it has to displace energy in other areas. You have to start exporting the electricity. This sort of falls apart at some point. I think that an extreme version of it is hard to get to because the energy has to be used somewhere, right? So you might be able to have small issues like this. It would be hard to get to a area that sort of negated all of the emissions reductions or something like that. That would be impossible. You can see small differences in the total amount of emissions based on where the displacement is occurring. Does that seem fair?
I think that's a very fair way to say it. I think that there could be more issues possibly in the interim periods as we're trying as that equilibrium effect that you're kind of describing is going to start taking place. That's fair.
Okay. Thank you so much, both of you, and also Sarah for joining us. Thanks for everybody who's stayed with us the whole time for the question and answers. please join us again next week. We're having another webinar. You'll be getting an invitation to that. I know I didn't get to everybody's questions. I apologize for that. Please go ahead and email us when we send around the slides. We'll send around the emails of the presenters and my email and Sarah's email, and we're always happy to be in dialogue with anyone out there. So thanks so much.